Comparisons of deep learning models for dynamic local climate zone mapping. Haoji Chen, Cho-hee Yu, and Chihao Wang. Introduction. The local climate zone concept, which provides an objective protocol for measuring the magnitude of any city's climate and ecology, has been extensively used to address the limitation of using only urban and non-urban for urban climate and ecology issues. Shang et al., 2023. The building structure and urban morphology were characterized to 10 built types based on building morphology factors and combing information on the surrounding exposure and surface conditions of a zone. Zhao et al., 2022. Therefore, this terminology has a great potential for revealing urban land changes through the portrayal of urban morphological characteristics. In addition, the analysis of multiple megacities using remote sensing images becomes feasible given the Earth observation-based approach for classifying LCZ. Local Climate Zone, LCZ, was designed from the very beginning with the purpose of providing an objective protocol for measuring the magnitude of the urban heat island effect in any city. With this term, it is not necessary to restrict the discussion of UHI, urban heat island, to a distinction between urban and non-urban with just two options, Stewart and Oki, 2012. Standard set is divided into built types 1 to 10 and land cover types AG. Built types include categories 1 to 10, mainly distinguished by building height and impact. Land cover types are also used as a means of differentiation, including paved and hard-packed, concrete, steel, stone, tile, and concrete construction materials, and permeable land cover types, low plants, scattered trees. Land cover types include categories AG, which mainly distinguish between land cover landscape types, where the type of vegetation, height, species is subdivided, Stewart, 2012. There are 4 primary approaches to LCZ mapping, including the manual approach, GIS-based approach, Zhao, 2019, Earth observation, EO-based approach, Bechtel, 2012, Bechtel, 2015, and hybrid approach, Zhao, 2021. The EO-based UDAP method, for example, employs a standard workflow to produce LCZ maps using the same data source, Landsat 8, and classifier, random forest, while generating sample sets based on different regions, Bechtel, 2015. However, the accuracy of this method can be limited. In contrast, convolutional neural networks, CNN, have demonstrated superior performance compared to other supervised deep learning algorithms in remote sensing visual recognition, Zhang, 2016, Ma, 2019. In the field of LCZ mapping, CNN models have been found to outperform traditional methods, such as random forests, Yu, 2019. This chapter delves into the potential of convolutional neural networks, CNNs, in mapping local climate zones, LCZs, providing a comparative study against traditional mapping methodologies. We introduce a novel data processing technique involving a 32 times 32 moving window and demonstrate its efficacy over conventional approaches. Leveraging data augmentation strategies for balanced LCZ representation, we evaluate the performance of several established CNN models in the context of LCZ mapping. With an overall accuracy of 80% to 90%, our findings highlight the promise of CNNs for future advancements in urban climate studies. Methodology. There are 4 main approaches for LCZ mapping: the manual approach, GIS-based approach, Zhao, Jensen, Wang, Currit, and Weaver, 2019, EO-based, Earth observation approach, Bechtel et al., 2015, Bechtel and Danik, 2012, and hybrid approach, Zhou et al., 2021. The manual method requires a lot of human and financial resources, not suitable for large-scale mapping needs. It is even less possible to analyze multiple cities. GIS-based approach. The basis for the GIS-based approach to map LCZ is based on values of geometric and surface cover properties, including sky view factor, SKF, aspect ratio, building surface fraction, BSF, impervious surface fraction, ISF, pervious surface fraction, PSF, height of roughness elements, height, and terrain roughness class, Stewart and Oak, 2012. Different research scholars have described these indices based on different data sources methods. Basic input data includes satellite and aerial imagery, land cover datasets, data with height information, road street maps, building footprint maps, and others. Oliveira et al., 2020, C. Zhao et al., 2019. The most used methods are the transformation based on existing land use datasets, Oliveira et al., 2020, See Zhao et al. 2019, and other standard datasets for reclassification, Hidalgo et al. 2019, and rule-based fuzzy preliminary classification using linear interpolation scores or ranks based on a representative set of metrics at the site, grid, subdistrict, or block level. Kotharkar and Bagad, 2018, Lelovics et al. 2014, Kwan, 2019. GIS-based methods are often inseparable from data with elevation information, e.g. NDSM or 3D city models, because elevation data are directly or indirectly related to SKF, ISF, BSF, PSF, and height of roughness elements, see Zhao et al. 2019. The open-source DSM and DEM data are both too coarse in spatial resolution and additionally cannot be analyzed over multiple times, Zhao et al. 2021. Precise point clouds can be obtained from LiDAR data to obtain NDSM elevation information, but due to its expensive equipment and cumbersome processing procedures, it is often used for small-scale measurements and usage. Although some cities or tracts have obtained airborne LiDAR range data, it is still difficult to obtain for the rest of the cities, and it is even more difficult to obtain at different times. See Zhao et al., 2019. The disadvantage of using the LULC data for conversion to LCZ is that the definition of land use data varies from place to place, and there is no way to develop a uniform method for conversion. See Zhao et al., 2019. EO-based approaches. EO-based approaches currently use machine learning methods for classification, which are classified as object-based approach and pixel-based approach. Object-based classification requires a lot of operations, more detailed information, and contextual knowledge, M et al. 2021a, M et al. 2021b, while the pixel-based approach can ignore some details and classify use pixel blocks, which is widely used in LCZ classification, Bechtel and Deneke, 2012. The approach involves selecting and solving the feature vector to describe the most accurate and comprehensive information in advance based on the features of the EO observations to classify the LCZ, and then using classifiers to judge the feature vector, the main classifiers being random forests, support vector machines, and so on. Bechtel et al. 2015, Bechtel and Deneke, 2012. The method of selecting the different characteristics of Earth observation data and their best fit with LCZ observations has been studied by research scholars, Bechtel and Deneke, 2012. The UDAPT method has developed a standard workflow for producing LCZ maps, which uses the same data source, Landsat 8, and uses the same classifier, random forest, but can produce sample sets based on different regions, thus allowing scholars to produce LCZ maps that meet their needs based on their own study area, Bechtel et al. 2015. In contrast to deep learning, the UDAPT method of shallow learning is used by a wide range of researchers because it is computationally convenient, takes less time, and is less complex. However, this method is often not very accurate, R. Wang et al., 2018. Hence, many researchers have attempted to map the LCZ using multi-source Earth observation data sources, such as Sentinel-1, La, Bagan, and Yamagata, 2020, and Sentinel-2 data, Shi and Ling, 2021, NTL data, visible light emerging from the Earth at night, La et al., 2020, and so on. The multi-source data make the accuracy improved, but the ease of data acquisition raises the difficulty. Hybrid models. The hybrid model combines the advantages and disadvantages of both GIS-based and EO-based approaches. It has been verified by scholars that the accuracy of the LCZ maps obtained by the GIS-based method is generally higher than that of the UDAPT method, R. Wang et al., 2018. The main reason is that the GIS-based approach is able to operate strictly according to the rules of the LCZ land cover attributes. And because of the different data sources, the LCZ blocks are represented in different forms, e.g. vector data and grid areas, which enables to obtain sufficient size and boundaries for each LCZ class, Kotharkar and Bagad, 2018, Oliveira et al., 2020. The biggest drawback of the GIS-based approach is that data sources vary in quality and format, and even the methods of conversion are developed based on specific data sources, Kwan, 2019. Some of the data are not global, and data acquisition becomes difficult if we change the study area. Although the MUDAP method is very simple and convenient for more research scholars to be used in many research areas, the disadvantage is that the method of UDAPT is a supervised learning method, which requires manual judgment of the class of training samples in advance, and the quality of label data very much affect the final results. In a grid block, different types of land use and land cover types are often mixed due to the dense characteristics of the city, and the criteria for labeling by different scholars are also different. Kwan, 2019. Some scholars, in order to synthesize the advantages and disadvantages of the above two methods, propose to use EO observation data for LCZ classification while combining GIS data such as OSM data to help segment LCZ blocks, which has greatly improved the final classification effect. Fonte et al., 2019, Shi and Ling, 2021, R. Wang et al., 2018, Zhou et al., 2021. Convolutional neural networks CNN models. Convolutional neural networks, CNN, have been shown to outperform most deep learning supervised algorithms in the field of remote sensing visual recognition, Ma et al., 2019, Zhang et al., 2016, such as scene classification, Hu et al., 2015, Scott et al., 2017, Yuan, Han, Gu, and Yan, 2021, target detection, Shin et al., 2016, Semantic Sagao et al., 2019. With its powerful ability to extract highly abstracted, generalized features, CNN models have been tried in the field of LCZ mapping and proven to be better than methods such as random forests, Yu et al., 2019. SO2 LCZ42 provides a standardized dataset of 42 city clusters worldwide, plus 10 smaller regions, resulting in approximately 500,000 pairs of Sentinel-1 and Sentinel-2 image block data, and a carefully designed evaluation process resulting in an overall confidence level of 85%, Zhu et al., 2020. Several studies have shown that training with the SO2-SAT LCZ42 dataset can be trained to obtain better classification models. Chunping, Schmidt, Lichao, and Xiaoxiang. Chu et al., 2019, Chu et al., 2020, Zhou et al., 2021. Most of the CNN models used for LCZ classification are adaptations of classical models, such as VGG, ResNet, etc. X1 Li 2021, S. Liu and Shi 2020, Chu et al. 2019, Chu et al. 2020, Yu et al. 2019, Zhou et al. 2021, while most of the models are trained from the initialized parameters. It is undeniable that none of us can prove the superiority of the models designed by the authors. Some scholars are beginning to recognize that completely designing and training CNN models from scratch is very challenging because it requires large amounts of data and takes a long time, Yuan et al., 2021, and that CNNs pre-trained on large datasets have general feature extraction capabilities that can be transferred to regions with smaller amounts of data, Shin et al., 2016. Many scholars have applied migratory learning for scene classification, and they have explored the effects of different depth levels of features on migratory learning, as well as the effects of different learning modes, parameter freezing, fine-tuning, initialization from random, on migratory learning results. Hu et al., 2015, Piers de Lima and Marfert, 2019, H. Zhao, Liu Zhang, and Liang, 2019. However, no scholars have tested in detail the best patterns and classifiers for migration learning for LCZ classification. In summary, the CNNs-based approach is able to obtain a more generalized LCZ classification model by training. This will be far different from previous GIS-based and shallow learning-based methods, as GIS-based methods usually have a small number of fixed-time data sources, and shallow learning-based methods usually have a small number of training samples. In particular, CNNs-based methods based on migration learning can lead to a very generalized model, which makes it possible to study the temporal variation of LCZs at the urban scale. However, the CNNs-based approach still suffers from low accuracy and a discrete distribution of classification results. In this paper, a variety of CNNs models are tested using a migration learning approach in order to obtain a more generalized model that can enable the study of the temporal variation of LCZs at the urban scale. At the same time, experiments are carried out to obtain high-accuracy CNNs models. Data processing and CNN models training. In our scheme, we considered the surrounding areas around the focal pixel using a moving window of size 32 times 32 at 32 pixel intervals. This approach resulted in better results than the RF-based scheme and other CNN-based schemes, e.g. 10 times 10 size feature extraction block, U, 2019. To ensure an equivalent number of polygons and patches of different LCZ types and independent LCZ types from each other, we utilized data augmentation in each polygon, i.e., by rotating 90 degree, 80 degree, and 270 degrees. Polygons refer to manually annotated polygonal regions that are homogeneous in nature, and batches represent a 32 times 32 pixel block. A list of the training and test datasets of LCZ types for each city is provided in Table 15.1. This study tests the traditional CNN models, including VGG, Simonian 2014, ResNet, He 2016, DenseNet, Huang 2017, and GoogleNet, Szegedy 2014, to obtain accurate LCZ maps of the 4 megacities and synchronously perform the massive LCZ classification more swiftly. All initial parameters were sourced from the official pre-training parameters, the learning rates were set to 0.01, and the entire training lasted 100 epochs. This study reclassified the LCZ types when calculating the overall accuracy, OA, to obtain highly precise results in classifying the 3 urbanization processes. OAX, OA high, and OA compact were calculated to indicate the OA of the 3 urbanization processes, namely, new urbanization, intensified height, and intensified compactness, respectively. OA equals with 3 cases, OA sub x equals n sub x divided by n sub m, OA sub high equals n sub high divided by n sub m, OA sub compact equals n sub compact divided by n sub m, where NEX, NI, and n compact indicate the numbers of accurately judged samples for LCZ type of new urbanization, intensified height, and intensified compactness, respectively. NM expresses the total number of all samples. Since its introduction, convolutional neural networks, CNNs, have been widely used in image classification due to their powerful ability in extracting abstract features, Zhang et al., 2016, and many related models have been proposed and performed well in the standard dataset ImageNet, including VGG, ResNet, SqueezeNet, DenseNet, and GoogleNet. Each model has its own characteristics. Table 15.1, Training and Test Dataset of each LCZ type by city. VGG is one of the most classic neural network models using small convolutional kernels 3x3 to extract more complex information than the previous large convolutional kernels 5x5 and 7x7. VGG consists of multiple blocks, each consisting of 2 or 3 convolutional layers, and a downsampling or pooling layer, which allows features of different depths to be extracted. The feature extraction layers are followed by 3 fully connected layers to classify the final result, Simonian and Zisserman, 2014. In this paper, the input layers, 3 times 225 times 225 to 7 times 32 times 32, are modified for the application. VGG is mainly divided into VG13, VG16, and VGG19 according to the depth of the network. ResNet uses a residual module to enable the network to be trained more deeply. Through the VGG model, scholars found that deeper networks can extract deeper features and information. But if too much training will also appear overfitting phenomenon, in order to avoid this phenomenon, ResNet adds a residual module so that the gradient can be passed between the front and back layers of the network, He et al. 2016. In this paper, the input channels are changed to 7 channels. ResNet is divided into ResNet 18, ResNet 34, ResNet 50, ResNet 101, and ResNet 154. SqueezeNet. SqueezeNet uses the FIRE module to encapsulate multiple convolutional and downsampling layers, consisting of squeeze, 1 times 1 convolutional kernel, and expand, 1 times 1 convolutional kernel, and 3 times 3 convolutional kernel, Iandola et al., 2016. In this paper, the input channels are changed to 7 channels. SqueezeNet includes SqueezeNet 1.0 and SqueezeNet 1.1 versions. DenseNet, as mentioned earlier, in CNNs, the gradient disappearance and overfitting problems become more and more obvious as the depth of the network deepens. ResNet proposes a residual module that enables the fusion of the front and back gradients within the module, but cannot fuse features that span large distances. DenseNet continues the idea of feature fusion by fusing the features of all modules and trying to ensure that layer-to-layer DenseNet continues the idea of feature fusion by fusing the features of all modules and trying to ensure the maximum continuity of information between layers. Ji Huang, Liu, van der Matten, and Weinberger, 2017. In this paper, the input channels are changed to 7 channels. DenseNet is mainly divided into DenseNet 121, DenseNet 161, DenseNet 169, and DenseNet 201. GoogleNet is composed of several inception modules, and the inception modules internally fuse features from multiple convolutional kernels, 1x1, 3x3, 5x5, and this approach enables the fusion of different scale features, Szegedy et al., 2014. At the same time, the deeper the network is, the larger the proportion of 3x3 and 5x5 is, the more abstract features can be extracted. In this paper, the input channels are changed to 7 channels. LCZ mapping results. The performance evaluation of various convolutional neural network CNN models for Beijing is presented in Table 15.2. Case of LCZ classification results for the Beijing region are shown in Figure 15.1. The models include DenseNet 121, Table 15.2, the performance evaluation of the CNN models for Beijing, demonstrating high overall accuracy OA ranging from 80% to 90%. Figure 15.1, LCZ classification results for Beijing. A and C indicate the references of 2000 and 2020, respectively. B and D indicate the LCZ classification results of 2000 and 2020, respectively. GoogleNet, ResNet 50, VG16, and VGG19. These models demonstrate high overall accuracy, OA, with values ranging from 80% to 90%. The DenseNet 121 model achieved an accuracy of 82.43% in the first instance and improved to 85.29% in the second instance. GoogleNet's performance was slightly better, with accuracy scores of 86.03% and 85.48% in the first and second instances, respectively. The ResNet 50 model's performance was consistent with accuracy scores of 84.20% and 72.8% in the first and second instances, respectively. The VGG16 model showed a decrease in performance from the first instance, 84.5% accuracy, to the second instance, 80.47% accuracy. Similarly, the VGG19 model's performance decreased from 83.24% accuracy in the first instance to 72.95% accuracy in the second instance. The performance results across the models suggest that GoogleNet and DenseNet 121 provided the most reliable and consistent results in this assessment. Discussion and conclusion. In our research, we examined the performance of various classical convolutional neural network CNN models, including VGG, ResNet, DenseNet, and GoogleNet, in local climate zone LCZ classification tasks. In our experiments, we found that DenseNet and GoogleNet provided the most reliable and stable results in our tasks. This could be because these models effectively integrate features of various scales and ensure the maximum continuity of information between the layers of the network as much as possible. Particularly, DenseNet, by integrating the features of all modules and trying to ensure the maximum continuity of information between the network layers, solves the problems of gradient disappearance and overfitting in deep networks. Compared to that, although VGG and ResNet also showed high accuracy in some situations, their performance varied between the two instances, suggesting that they may not have the stability of DenseNet and GoogleNet. Huang, 2021, Li, 2021. However, it is important to note that all these models perform well in our tasks. Their performance may vary in other tasks. Yu, 2022. Therefore, we recommend researchers to choose the most suitable model based on their specific tasks and data. In summary, our research shows that by using suitable CNN models, we can effectively classify and map local climate zones, LCZ, and further understand the process of urbanization. However, to optimize performance and accuracy, it is crucial to choose the most suitable model and tune parameters. Future work might explore more models and methods to further improve the accuracy and efficiency of LCZ classification. Liang, 2023.